All right, thank you so much, and welcome everyone to the Barefoot session of the Networking Field Day 23. We've been presenting at Networking Field Day for a few years now, and it's always a pleasure and a joy to be back here. Today, we're going to be talking a little bit about how do you unlock some efficiency in your network with end-to-end, telemetry that is extracted real-time and also in a programmable fashion across switch, NIC, and the CPU, right? So we started out with the switch, and we went to the NIC, and now we're going into the CPU. All right, as people are, trying to deploy applications, in much larger compute clusters, connectivity becomes really critical. And in some cases, actually, connectivity can be the bottleneck because the compute side, things are getting more and more powerful, but then shuttling the data between all these compute nodes can actually be a problem in some cases. So, what we're trying to say here is that connectivity is really critical for unleashing compute performance at scale, right? We're living in a world of distributed connected compute, so the connectivity piece is really critical. And what I'd like to say is programmability is really critical to connectivity to actually unleash this compute performance, right? So that's where we'll be focusing this talk on. A quick refresher, Barefoot Networks, as you know, was a startup, got acquired by Intel, mid last year, and it's been a little over a year. We have had Tofino and Tofino 2 switch silicon, shipping, and we have also software products that we deliver to our customers. P4 Studio is our software development environment, and P4 Insight is a debug tool which helps people debug their P4 programs. And Deep Insight is our network performance and monitoring and analytics software. So I'll touch upon these things as I go through this presentation. So feel free to stop me if you have any questions. Looking a bit closer at the silicon portfolio, the switching ASIC portfolio, we have multiple SKUs in each family, Tofino and Tofino 2, ranging from 1.2 terabits all the way to 12.8 terabits per second. And the cool thing is all of these switch ASICs are fully programmable using a programming language called P4. And it allows the end users to customize the pipeline to their specific needs, or vendors to customize the pipeline to their customers' needs. So that's really the innovation and the power that we brought to the networking industry. There's still some questions out there. People wonder, why do we need a programmable pipeline? I don't think we can imagine a world in the compute industry where somebody would say, I want a fixed function CPU. We kind of take it for granted that the CPU is programmable. And I think that's what will happen in the networking world too. We have definitely brought some technology into that space with our Tofino switching ASICs. But if you look at it, right, like any fixed function ASIC will have all the protocol processing, baked into the silicon. So if you need more features, you have to wait for the next rev of the silicon, and that takes a few years. I mean, this is not news. But when you have a programmable ASIC like Tofino, you can actually specify the processing logic in software and download it into the Tofino ASIC, right? So without any hit on performance, without any hit on price or power or things like that. So that's really the innovation, and that actually enables our end users to kind of create what they need rather than try to fit what a vendor is giving into their network. right? So that's really the power of the programmable pipeline. So when you have a programmable pipeline, you need to have a programming language, and you need to have an open programming language, and that is P4, which we helped co-create along with Intel, Microsoft, Google, Stanford, and Princeton. And it's really encouraging to see how this ecosystem has started out small and kind of, really grew into this huge force, where almost all the who's who of the networking industry is taking part in this ecosystem. They're members of this organization at Open Networking Foundation. Lots of developers, mostly in the networking industry, being trained on P4 so that they can actually define the data plane off the chip themselves. And then also we are seeing adoption by other vendors, Swiss silicon vendors, SmartNIC vendors adopting P4 to describe the data plane code for their targets. So it's a very vibrant and growing ecosystem. Definitely check it out at p4.org. So now when you put these two things together, this open language, which is domain specific to networking and packet processing, and a really high performance switch silicon, which is fully programmable using this language, you can create all kinds of wonderful new things. The switching use case is like the standard use case, so which can be done pretty easily. But we are also seeing customers take this platform and create new things out of it. Things like network packet broker, load balancers, even traffic testers, gateways, and more and more packet processing workloads like UPF and BNG are being explored. So Tofino itself can do all of these things, but then we're also seeing combinations of Tofino and Tofino 2 along with an FPGA. And when you combine these devices together with the Intel CPU, you have a really powerful combination, and people are doing really interesting things with them. It brings you lots of benefits, of course, performance benefits, lower power, deterministic low latency because it's a pipeline architecture and it's programmable. And you can do software upgrades to your hardware in the sense that you can deploy a new P4 program into this platform and it can do new things. So it's really powerful. So when we created this software development environment, we also made sure we give the developers the tools that are necessary to be able to develop these programs quickly. So one of the tools the developer needs is a debugger, right? So P4 Insight is an advanced debugging utility, which helps you visualize your P4 program and how it maps to the Tofino pipeline. So it makes it really fast for people to not only develop the code, but also debug it. So, there's been a lot of talk about, what are the benefits of programmability, what are the use cases. We've looked at a few, but one of the key innovations about this is the ability to get real-time visibility into what's actually happening on the data plane. So we kind of helped co-create this technology called In-band Network Telemetry, which you're probably familiar with. It's the ability to take the real-time metadata that's associated with a data plane, whether it's in a switch or a NIC or a software data plane on a CPU, and package it up and send it to a collector for analysis and intelligence. So this is an open standard published through the P4 project, and all the formats are published there, so you can take a look at it. And the headers can be placed in such a way that they don't mess with intermediary devices that don't understand INT. So you can put them after a layer 4 header, or you can make them part of an extension header, or you can even overlay it on some fields if you'd like. Tofino can do all of that because it's fully programmable. So we basically take the spec and implement whichever way seems best for us, right, and for the customer. So yeah, you have this switch NIC and CPU and software data planes generating this rich telemetry that's real time. Now it has to go somewhere to be analyzed, and that's where Deep Insight comes to picture. So Deep Insight is a network monitoring and analytics software that consumes all these telemetry reports from different data planes, and collates the information, does analysis, and then gives you dashboards and troubleshooting mechanisms to kind of go look at this information and make some intelligent decisions on what's going on in the network. Some of the things are listed here, path and latency tracking, proving that packets for a particular flow are going through a particular service is becoming quite important. So you can do that with path and latency tracking. Understanding packet drops, of course, is quite important too, which we can do. And also understanding how congestion is happening in the network and where congestion is happening and why it's happening, who's the aggressor flow, who's the victim flow. I mean, all of this data can be, gathered through this In-band Network Telemetry feature and in conjunction with Deep Insight. So Deep Insight itself is it's a big data pipeline. It has a collector that collects all this information. There is a database that stores this information in. It runs analytics on it. So lots of intelligence in Deep Insight, but we are also giving ability for third-party, software vendors to kind of pull this intelligence from Deep Insight using a REST API. So we have a third-party streaming REST API that people can integrate their applications, monitoring applications, and glean the intelligence from Deep Insight and integrate it into their dashboards. So we also help with that. We also do data retention for historical analysis. So you can actually go back in time and see what happened in the network at a specific time. So the whole experience with In-band Network Telemetry and Deep Insight started out with switches, with Tofino and Deep Insight. And then we've started adding the In-band Network Telemetry capability to FPGA-based smart NICs. For example, our Intel PAC N3000 smart NIC, which is an FPGA-based smart NIC, also has INT feature working on it with the Netcope P4 compiler. And more recently, we have actually enabled INT capability in Linux using XDP and TC, and also a VM. So we have options to export the In-band Network Telemetry, information from the server itself. So we're kind of, increasing the sphere of visibility, not just into switches, but also into NICs and into the software data planes on the server. And this is quite powerful because now you get visibility into an application flow right until the point data goes into the application. So you really don't have any blind spots for performance degradation of an application or forensics or proof of path and things like that. So it's quite powerful, and we're seeing a lot of interest and deployments from our customers for this technology. Another interesting thing that we are seeing is this ability to export metadata is not only about visibility, but it's also about improving network performance, like being able to do congestion control and make it really efficient. Being able to do some workload acceleration in the network, application workload acceleration, and being able to do some network function acceleration. Right? So these are all possibilities because of this programmability of these data planes, as well as the visibility that you're getting into these data planes. So now I'll go into a few examples of how some of our customers have done this, and then time for Q&A. So you may be familiar with this use case. This is a use case that Alibaba has publicly talked about last year. They've actually published a paper on it, but they had looked at all the different congestion control mechanisms and were convinced that it could be done much better. And so they have come up with an algorithm called high precision congestion control, which basically uses the in-band network telemetry feature to kind of communicate the bottlenecks in the network back to the sender so the sender can adjust the transmit rate. So by being able to do this, they are getting near peak utilization of the network and keeping the network from going into a state where there are packet loss and drops happening or congestion happening. So with this feature, they were able to improve the network performance astronomically compared to all the other congestion control mechanisms, and basically use the network infrastructure that they have already deployed to the maximum level possible. So really fascinating. The paper is there, so there's more details in that paper. Another interesting use case is one of our customers, Softbank, has actually taken a Tofino-based white box and have written a P4 program to perform the network packet broker functionality. So they needed this network packet broker to kind of go look at the inner 5-tuple of the GTP tunnel packets, and then do load balancing on that, and then do some kind of traffic engineering on that on the traffic, but based on the inner 5-tuple. So they were able to parse these packets using the P4 program that they have written and Tofino, and compute this hash with the inner 5-tuple, do load balancing, and they were able to actually deploy this. Right. So it's really interesting to see our customers being able to take the advantage of P4 programmability into their own hands and then come up with really revolutionary things like this. Okay, little announcement here about one of our OEM partners. Arista has the 7170 series, which uses Tofino-based Tofino silicon in it. So they have 3 models listed there. But they've actually shown how an OEM can take the Tofino silicon, a programmable switch ASIC, and kind of innovate on it, right? So they have been able to kind of deliver features that they couldn't deliver on other platforms, which are based on fixed function ASICs. So it's really great to see our OEM partners like Arista take advantage of the programmability and implement new and innovative features on the standard switching platforms and deliver it to their customers. So there's lots of details there on their website, and there was also a recent webinar where they went over these features like CGNAT and server load balancing, all done on the Tofino switch ASIC in their platform. So now, scaling beyond from where we are to 25.6, 51.2, and 100 terabits speeds, right? One of the things that becomes really important is when you go to those speeds, the cost for getting the bits out of the switch will be astronomical, not only in terms of cost, like dollars, but also in terms of power. So co-packaged optics will become more and more important and necessary as we scale to these speeds. And, after we became part of Intel, one of the things that we started doing is this co-packaged optics exercise with Tofino 2 and our photonic engines from the Silicon Photonics Products Group. So in March of this year, we actually did the industry's first live demonstration of Tofino 2 with integrated with the photonics engines, 1.6D photonics engines from our Silicon Photonics Products Group. Running real traffic. We've done a big announcement and launch, and it's pretty clear the power savings and the cost savings people will get from this technology. So In this particular case, we're actually showing not only photonic integrated circuits integrated into the chip onto the package, but we are also using electrical connections on the same package. So you have a choice of both optical as well as electrical coming out of the same package to the front panel. So lots of innovation happening in terms of technology integrations, on the switch platform. And where we're going is being able to take this P4 programmability to basically everywhere in the network, right? So we have all the components, we have the technology. Now we're turning on this P4 programmability across all these components. So you have this network that is really agile, network that is programmable, and helps you implement the things that you need to implement. And not only that, but implement them where you need to implement them, right? So in the location of the network. So that's essentially, what I wanted to cover today. And if there's any questions, I'll take them.
I was hoping to maybe save this for some after discussion, but where's a good place someone could maybe just begin to learn more about the basics of P4?
Oh yeah, that's definitely a great question. The p4.org website has some information on it. There's a getting started section there, and there's quite a few tutorials. If you go to the blog section, I would go to the blog section of p4.org, and there's actually quite a few tutorials with virtual machines that you can run your P4 program on, and sample P4 programs and things like that. And also a lot of the P4 related events that are happening across the world will typically have a P4 tutorial. And so that's how the community is growing. There's all these, for example, there's one coming up in Japan later this month. It's like a P4 users group, and there's probably going to be a tutorial there. But yeah, a good place to start is definitely p4.org and the blog section there. Open Networking Foundation also has a page for p4.org, so you can go check for resources there at opennetworking.org. So those are some two places I would say you can go check out.
As we were going through the queuing and then into the DDP and passing through the NVMe OF on the way, I was sitting there and thinking, my goodness me, we're packing a heck of a lot into these Ethernet controllers now. So it really does seem there's an awful lot of this offloading going on. So there's clearly, it's another one of these step changes, much as we got when we came along, I guess, with things like DPDK, kind of that step up in performance of networking and CPU working together. To get another level up in performance. It seems like there's an opportunity there for yet another step up of optimization between the Ethernet controller and the CPU to improve the communication between the two. And it's funny, as DDP was being described, I was sitting there and going, this is sounding an awful lot like ADQ. And I was kind of surprised at the end to hear that it wasn't, and actually you were looking at that as as possibly something that it could be in the future. So I guess it sounds like DDP's been around longer, so maybe that's a future thing. But yeah, it's very cool seeing all this stuff coming into one place. So just an observation. Very cool. Very cool.